Okay, great. So yeah, thanks everyone for coming to my talk. And I'd like to thank the organizers for letting me to speak about this quantity which is computed for any tripartite quantum state. Yeah. Oh. Okay, so yeah, so this talk is about this quantity which we call the modular commutator. Is defined on any tripartite quantum state. From there, you can tell the quantumness and chirality of the quantum state. I'll be mainly tell you about three related things we learned recently in this work. This work I collaborated with 4 people. All of them are somewhere at Northern California. So Yijian, Jonathan Sauce, Ian, Tam, and Ada Kim. I'd like to start with a very general and basic question. So why are we interested in many-body systems with the entanglement? So entangled quantum many-body system, this quantum state. Why are they interested? So I guess everyone in this room have something to say about this, because both condensed matter systems and quantum field theory are such systems. So they all have many degrees of freedom. So there can be some distinction, like in condensed matter theory, usually space is kind of looks different than time direction, and in quantum field theory it's easier to relate those two. So those are space and time are usually treated on equal footing. So here's the space-time diagram for the conformal field theory, where the quantum state is defined on a Cauchy surface, which is a space-like surface, but it can be bended. It's doesn't have to be a time slice. And another useful way is to think about the causal diamond. So, but yeah, the important thing is that both are many-body systems, so there are many particles. So we should feel free to divide them into different parts and talk about the entanglement and yeah, the quantumness of the state. So yeah, instead of telling you directly about the new formula, we either derived or conjectured. I'd like to start from reviewing something about quantum entanglement. This page is really basic. I think everyone knows it, but gradually I want to hopefully to tell you something non-trivial about entanglement. So yeah, what do people know those days? What have people learned during the maybe past 20 years about quantum entanglement? This is just a sketch. I'm not going to tell you everything, but so in terms of a quantum state, we want to know what is really quantum. So usually a quantumness gives rise to many different quantum phenomena. Those phenomena, some of them are very hard to understand. So that's part of the reason we are interested in entanglement. We can hope to discover the reasons for those non-trivial phenomena to occur. So for that purpose, I'd like to first tell you what's the classical state. The classical state, in this page, it's for any bipartite quantum state, real AB, can be mixed state. But the important point is that classical state, in classical state, there is a preferred basis choice, and there is a probability distribution. Those are real numbers, and that's it. So there's nothing else in this state. For any classical state, the entropy is non-increasing when we reduce to the subsystem. So if we do a partial trace and get to subsystem A, the entropy is always smaller or equal to that thing. So for bipartite bipartite pure state in quantum mechanics, if the state is quantum, then there can be entanglement. So yeah, a simple fact is that if we have a classical pure state like this one, psi AB, then yeah, if it's classical, then it's a product state, so it's not so interesting. So quantumness is characterized in this case by the von Neumann entropy. Yeah, this is should be familiar, but now let's look at what von Neumann entropy says for quantum many-body system. So not only can the state tell whether the state is entangled or not, it's well, in other words, whether it's quantum or not, it can provide us with some insight on the phase of matter. Yeah, actually, it can tell us many things, but here are the something people consider during mostly during the past 20 years, like on the ground state, finite temperature state, and some state in the some dynamical setups. One such example is the conformal theory in 1+1 dimension. So if we take a single interval A, the entropy for that single interval is a constant. Well, C is the central charge, and L is the length of the interval divided by a cutoff. So there's the logarithmic scaling law. On the other hand, for gapped system, it's proved in one dimension, but it's believed more generally that gapped many-body system had entanglement area law. Not only that, so for 2+1 dimensional topological order, the subleading term is also interesting. It's a universal constant, which tells you how many anions are there in this system. Yeah. Yeah, you see the topological entanglement entropy is a linear combination of entropies. So actually, we cut the system into more pieces, but still, each term is just yeah, entropy for which is the entanglement measure for a bipartite pure state. So yeah, you may ask, oh, well, linear combination actually is a good idea. There are other important quantities we can just write down using the linear combination of entropies. This page are a few of them. One is the mutual information, yeah, on A and C, which actually tells you about the total amount of correlation between A and C. So it doesn't directly measure the quantum entanglement, but it's a sum of quantum entanglement and classical quantum correlation and classical correlation. Another is called conditional mutual information. And there is a very powerful non-trivial formula called strong subadditivity, which can tell you some constraint using that quantity. So there are one more which will be used quite often in entanglement bootstrap. So I will not tell you about it because John McGreevy will talk about it tomorrow. Okay, so far those are still bipartite. Well, the entanglement characterization for bipartite pure state. The natural question is, are there other things like you know, the state has many particles, they are entangled in some way, so we want to extract the non-trivialness of the quantum state are the entanglement entropy and the linear combination. The only thing we interested are there other things? Yeah, the answer is actually positive. So the next the simplest thing is a bipartite mixed state. So in the quantum information, yeah, quantum information people had some sense of unentangled mixed states. That's rho AB. So written this way, it's called separable state. Entanglement monotone are some class of entanglement measures which characterize the difference between a quantum state to a separable state. So there's no unique choice, but there are a lot of them, different choices. Those are the quantum information papers introduce those entanglement measures, and there are a lot of physical applications. Again, I won't go into any detail because there's a panel discussion tomorrow. In particular, I think Tyrone did some of the early application of those things to many body systems. So he probably want to say something. Another interesting feature appeared for mixed state is that separable states, so the so-called unentangled mixed states are actually not classical either. So they can be useful for some something like quantum interferometry. So there's some of the states are actually quantum. So we need to be careful. There's actually a lot to explore in this direction, I think. Okay. Yeah, I hope that had convinced you that the story of entanglement is kind of rich. It's not just about entanglement entropy. Then how about generalization? So how about tripartite mixed state? This sounds like an obvious direction to generalize, right?
Sorry, could you say what you meant by a subset of separable states is classical?
Oh, okay. So okay, Apet had a question saying he wanted me to explain what's the difference between separable state and classical. So okay, great. So the classical state, classical state means that we have some preferred basis choice. Yeah, let's take a look, take this as an example. So the state rho AB on the left has some preferred basis choice I. So I is some fixed also normal basis on A. So that makes it more special than the generic separable state, because for generic separable state rho A I it's a general density matrix. It doesn't have to be written in that basis. It must be a pure state rotated in a different basis. Sorry, in a different direction. Like the one on the left is a spin up and spin down, but the one on the right can be the spin pointing anywhere on the block sphere. So,
why does that make a
difference? That's not so easy to explain. I'd recommend you to check this paper. And there are other interesting papers which I discovered last week, actually. Yeah, thanks. Great question. Okay, so tripartite mixed state. This sounds like an obvious direction to do the generalization, but the real question is whether there can be intrinsically new insight. I'm going to argue in the rest of my talk that the answer is yes, there are some new insight, and that thing is at least one such thing is chirality. So in particular, there's this modular commutator defined like a commutator of the logarithm of the reduced density matrix on AB and BC. So yeah, it's really just an expectation value, but that's the same state. So there seem to be three things of real is the density matrix on ABC. Yeah, I told you that there's a lot of things in quantum information theory literature. You may wonder, like, can we look it up? It turns out we wasn't able to find a reference for this quantity. Why did we consider this quantity? We were trying to solve a puzzle about chiral central charge. So that's a physical puzzle, and somehow we tried this one. When we wrote down this one. When Isaac wrote down the commutator, at that time we know very little about this quantity. We did not know whether this thing has a very good information theoretical properties. We basically know nothing, but we just have to try it. We need to explore and find out how nice this thing was. And here's some properties we discover after playing with it. So J is an invariant under time reversal. That's take the state to its conjugate, and J is an odd under the switch of A and C. Those are abstract version of time reversal symmetry and space reflection, and it can tell the quantumness of the state. The J is non-zero only if rho ABC is well, it's zero if only if J is rho ABC is real. In other words, J is always zero for classical states. So in other words, the non-trivial signature only appears for quantum state. Yeah. And yeah, some other important properties include the fact that for quantum Markov state, that the state saturates the strong subadditivity inequality. For those state, J is zero. And there's a simple response function of entropy. So the response of the von Neumann entropy and the one parameter modular flow is precisely the modular commutator. And there's a lot more, and we are still discovering some other properties of J. Yeah, this is ongoing. Okay, so in the rest of my talk, I'll tell you about 3 applications. It's some formula we either derive or put or conjectured for some interesting physical manifold system of interest. Some of them are I think the distinction is not sharp, but I thought some of them are often considered to be condensed matter, and some are more interested to high energy people, like conformal field theory and gravity. Those are actually closely related. So I'll tell you how they are related. So those things I actually struggled a little bit in decide which one should I start to explain to you. But I'll start with the edge of topological order, because that's where I was standing in the beginning of our collaboration. So if Yi Jian gave you talk, Yi Jian is the expert of CFT in our in this project. So he may start from the 1+1 DCFT, which is I think is a equally good starting point. Okay. So for the 2+1D topological order, so why I'm how we started looking at the edge. So first of all, in our previous work, we proposed the formula for the chiral central charge. So this C minus is the chiral central charge for the 2+1 dimensional topological order. So that's not the chiral central charge for the CFT, but it's very similar. So X, Y, and Z are the union of them is a disk in the 2-dimensional block. So yeah, for that partition, we can derive this simple formula for the almost derive. We argued somewhere. So this simple formula for the disk in the block, so a simple question is how about the edge? So that there's actually a simple way to read.
Sure. I have a question. So from the definition of J, is it clear that divided by pi is always rational?
No, that's something we don't know. So yeah, that's an excellent question. So related to that, let me see a few more words. So here, the trace row A, B, C, log row A, B, and log row B, C. So in the definition of entropy, usually that log can be taken with any base. But this one, we particularly want it to be the base is the natural log, so it's E. So for precisely the reason that only when the left has that particular log can we have a pi/3. Otherwise, this thing looks more complicated. So this is very special. It's different from like topological entanglement entropy. That thing the log on both directions, and the 1D CFT, that formula also has log in both directions. So it doesn't matter which log we take, but this equation matters. So it's very mysterious. We really think it's a nice problem to try to derive. So can we say that, for example, can we just use entanglement entropy as the assumption and then show that the right-hand side must be pi divided by 3 times the rational number? Yeah, that's an open question. We don't know how to do that.
If this J is defining arbitrary space.
This okay. Okay, Shuhan's question is J defined on any space-time dimensions? Yeah, my answer would be yes. Actually, it's more general. We don't need space-time. We just need a tripartite quantum state. Great.
But in higher dimensions or in other dimensions, we don't quite have the analog.
Right. Yeah.
What is this?
Yeah, good question. So well, what I answered was that the quantity J, the modular commutator, was defined on any tripartite quantum state. But for this particular formula, we only derived for 2 plus 1D.
Do you have a guess on other dimensions? What does take? Responses are nice invariant.
To answer that question, you first need to tell you what partition you choose. Yeah, there's some freedom. Yeah, we can discuss that later. Yeah, great. Okay, so yeah, I started from the book, and yeah, at the beginning of the project, what interests me was that there's actually a simple way to convert this bulk partition to a boundary partition, and surprisingly, yeah, maybe not so surprising, but it's very interesting that we can derive a formula for a boundary partition ABC. So JABC is a pi/3 times C minus. But the most interesting thing for this particular formula is the fact that psi tutor doesn't have to be the ground state. It can be pure state with some boundary excitation. So as long as the bulk is the same with the ground state of the 2 plus 1D topological order, then we have this formula. So yeah, it doesn't matter. So even if we have some excitations on the boundary, that sounds interesting to me. So yeah, but and okay, here is a sketch of the proof. So yeah, how do we say that? Why the boundary doesn't play much role in this formula? The reason, intuitive reason, is that we can bound some entropy condition involved the boundary. So here, ABC has a is on the boundary, but we don't need any conditions on the boundary to derive this quantum Markov chain structure. So we need some BCD in the bulk. Yeah, we know some condition on BCD, then we can say something involves the boundary. So that's the strategy. Okay, and more interestingly,
excuse me, there is a related question. Can you compute the chiral center charge on the closed manifold, say on the sphere, not on the disk?
Yeah, that
state on the sphere.
Yeah, that's possible.
So similar partition, something like that. Then you have two vertex. One north pole, one north south pole.
are you saying that X, Y, and Z covers the whole sphere? Yeah, there yeah, let me see. There's one basic property of J is that so J is 0 for any pure state. Yeah, so if the tripartite state is
I
pure,
see.
then J is 0. So yeah, so
I see.
we want to
So
leave
maybe
some.
on the sphere, you do it if you, yeah, if you divide the sphere into 4 parts. Yeah. Okay.
Right. So if we partition the sphere into 4
Okay. Yeah.
parts,
Thank you.
then it's the same. But yeah, I think it's interesting to
Yeah,
ask, for
we
example,
can do it.
partition of the torus into 4 partition. Actually, in that direction, there are some open problem. There's some partition we don't know how to compute. So yeah, I think it's generally a good question to ask about
Okay.
the different partitions. Yeah, great. So okay, so let me continue with the result B. So this is well, it's some simple question we can ask, like to reduce A, B, and C further. So it's a ABC kind of like an interval times a shorter interval in the perpendicular direction. How about that? So yeah, we don't know how to derive it. So at the beginning of the project, we tested numerically for free fermion. We only tested for free fermion, but there's a good reason for that. Only free fermion can go to very large length scale. So free fermion, other interacting model, it's hard to go to large length scale. Like we cannot have many sites, so it's hard to tell the dependence of the cross ratio. But it turns out for the free fermion we tested very accurately that it's just beta to the first power. Yeah, we were surprised. Yeah, why is not other functions of eta? There might be some other good theoretical theoretical explanation for that. So we explored further so that give the second story. So the second story is on 1+1D CFT. So if we reduce the density matrix from the disk, the system is on a disk to the annulus on the boundary, then obviously we get some mixed state. Yi Jian observed that this mixed state, well, which is effectively 1D system, effectively it has 2 temperatures. So one is suppose it's completely chiral, then the physical boundary is has only, let's see, left mover and at a 0 temperature, but the boundary we obtained by the partial trace has only right mover and at a different temperature. So effectively that's some chiral thermal state of 1+1D CFT. So maybe it's a good idea to separate them and consider chiral CFT. So yeah. So for chiral CFT, it turns out we can find this formula first numerically, then theoretically. So let's observe yes what it says. That 0 temperature, this is something with a cross ratio, but there's an actual 1 here, so it's a kind of slightly different. And at infinite temperature, it becomes topological. It's just the same number, always the same number. Yeah.
So continuing on the field theory, it's not completely precise finding density with the Hoover space.
Right.
And the issue is even more severe when you have gravitational anomalies.
Indeed.
So does that kind of subtly enter into the way you compute this?
Yeah, great. Shu had a question asking, so that the subtlety of conformal field theory in defining entanglement entropy and compute it. Yeah, I'll explain it in the next slide. Great. So okay, so here is this formula. So omega is the CFT vacuum. Interestingly, this formula appeared very recently in more than one paper. There's actually 2 other papers within 2 months to our archive. I think they all have a related formula, if not the same. But I can't tell you every approach of proving it. So, but I picked my favorite proof. It's due to my collaborator Jonathan South and Yi Jianzhou. The reason I like it is that it's purely geometrical. I'll try to answer Zhuheng's question when I describe it. So first of all, this is some formula we know in our previous work. And the modular flow, the entanglement entropy, if it's defined, then it's a minus G modular commutator. Then a simplification is that for conformal field theory, if AB is a single interval, then the modular flow is understood very well. It can be represented by a vector field in the space-time within this causal diamond. In other words, the domain of dependence of AB. It's just a vector field. So beyond the single interval, we cannot use this picture. So I think this is really we get very lucky on this. And the second, which is related to Zhuheng's question. So first of all, conformal field theory, from my understanding and reading the literature, so the Hilbert space structure is a very subtle. But first of all, it's an infinite dimensional Hilbert space, and it doesn't allow the tensor product. Those two things are already non-trivial. But luckily, there are some ways to take cutoffs and compute the entropy even for chiral theory, like this formula we found in one of the references. So maybe your question can be rephrased like how do they derive this formula?
So the entropy here is defined in terms of the modular operator?
Let me see. Epsilon. You mean the epsilons and U and V in this formula? Oh, okay, good. So those U and V's are light-like direction. So we can sometimes come using the space and time direction, but for some application like this one, it's more useful to choose the light count direction. So U is this right moving light count. U is the other light count direction. I think the power of this formula is that it can separate the two light-like direction, including the cutoffs. The cutoffs are on the light-like direction. If we suppose we take this formula and use our formula for the modular flow, we can derive it. That's the claim. That's what we did. Great. So I think I don't need to go to any details in this computation because you can already see it's purely geometrical. You can just look at how the vector field affects the intervals. One thing I want to mention is that the formula of entropy does not only depend on where the endpoints of the interval are located, it also depends on how the interval bends. Your local boost, the boost angle here plays a role. Because that this formula for chiral CFT was so simple, we asked some further question. One route for direction was actually this ADS CFT. We try to ask what happens if the conformal field theory has a gravitational dual which lives on ADS. presumably. Okay, so it turns out that we came up with this angle conjecture. So it's the right-hand side is a set of cosine theta and with some possible plus or minus sign. Yeah, to motivate this conjecture, here's the simplest case. So the simplest case is ABC 3 contiguous intervals on the vacuum. So the bulk view of the CFT vacuum is just the anti-de Sitter space, and it's almost trivial to verify that cosine theta is 2 eta minus 1. But yeah, maybe I should say there's a subtlety about the gravitational dual. So for the edge to be chiral, we need some gravitational transcendence term. So the gravity is not the standard Einstein gravity, but luckily it doesn't affect the some classical solution of this 2 plus 1D gravity. So that's why, yeah, that's not how it works. So yeah, so the vacuum works. So it's quite nice, but it's just one example. We can ask whether the angle conjecture is true more generally. The next example, yeah, is the BTZ black hole. So it's due to a high temperature state on the CFT. So if the temperature is larger, then the BTZ black hole is larger and classical, almost classical. So we can still draw geodesics. So it can intersect at one place. If it intersects at one place, we can still compute the result using the conjecture and compare with the CFT calculation. Yeah, you may wonder, why can we still compute? The simplification is that the BTZ black solutions in 2 plus 1D are just the quotient of the global ADS, because the 2 plus 1 dimensional Einstein gravity is topological. Yeah, there's a, yeah. Yeah, sure.
Which chiral gravity are you studying here? Pure gravity, or does it have other matter?
Okay, good. So the simplest, and yeah, maybe that's the only one I know, is so in the Lagrangian of the gravity theory, we have the well, Hilbert Hilbert action. So plus some constant times the gravitational transcendence theory in 2 plus 1D. That's it. Nothing else. Just no matter field. Yeah, just gravitational transcendence.
Right, but pure gravity in ADS probably doesn't exist.
You mean at the classical level or the quantum level? Yeah, we can talk about that. I thought at some parameter it's okay. But yeah, we can talk about it. I'm not an expert. I just read some reference for that. Yeah, I think at least for classical gravity, there is a paper, and for whether quantum is okay, I thought my understanding was that for some parameter it's okay.
But at least the dual extreme of CFT does not miss. Not.
Oh, okay. Yeah. Let's talk about it later. And
Maybe use 5 minutes.
Yeah, great. Yeah, I think I'll finish within 3 minutes. Okay, so so far those are something we can compute from the angle conjecture and compare with the analytic computation. Can we come up with other examples? One such example is the state with a partition with a pair of intersection angles theta 1 and theta 2. Yeah, we can do a computation from the conjecture and find out whether it makes sense. To do the comparison, we need the chiral thermal state for some free fermion CFT. So we need both left movers and right movers. So the left movers are in the vacuum, so the two geodesic doesn't have intersection angle. So all the contribution come from those thermal state and those two intersection angle. So that's a very clear signature formula we can derive. In comparing to numerical data, we found that the data and the prediction actually was agrees pretty much with each other when the temperature is high. So what do I mean by high temperature? In this case, beta, the inverse temperature is 0.15 of the total circumference of the system. Okay, that's completes my story. So here's the summary slides and some open questions. Thank you.
Hi, I don't really understand your formula. So you have a logarithm of a density matrix. So there are different branches of a logarithm. So you can add like 2 pi integer-based matrix to it. Why does it affect your formula? And the second question, you can have 0 eigenvalues for rho. And you can have rho can have 0 eigenvalues. So how you can take a logarithm of 0?
So okay, so the two questions are mainly about the logarithm of rho. So for a generic operator, taking logarithm is problematic. Luckily for rho, so density matrix rho, so it can be diagonalized, and every eigenvalues are either 0 or positive. So if all the eigenvalues are positive, then we can just take the logarithm of the positive value. In that case, the logarithm is uniquely defined. So in other words, in technical words, that's the logarithm of any positive operator is defined. So the second question is a little more subtle. That's what happens if rho has 0 eigenvalues? Then it's then it's not positive, but we can still add a small identity to it. So then it becomes positive. We can take the limit to define it to be the logarithm. Yeah, that's the strategy. I think it works theoretically, and also that's the way we compute logarithm in numerical method. Yeah, it's we do find. Sorry. Yeah, I think if the how about we write down some see whether it is. I actually don't remember. I checked the detail, but yeah, I think it should exist. But let's write down something on a piece of paper and see. Maybe it's more interesting if I'm wrong about this point. So let's talk about it afterwards. Thanks. Other questions? Oh. Okay, I think John has a question.
Yeah, sorry. Did you say that the modular commutator also does it vanish on those separable but non-classical states that you were talking about earlier? If you make a tripartite separable state, does the modular commutator vanish?
Okay, great, John. Okay, so John's question is okay. So here's a separable state, rho AB. So we can try to do the same thing for sorry. This is a bipartite state. We can do it for tripartite state and define the so-called tripartite separable state. The question is whether modular commutator is always 0 for tripartite separable state. That's a good question. I couldn't answer it until last week because I intended to put the title as entanglement measure as my talk, but I changed it because precisely because of the answer of John's question. It turns out if my numerical is correct, then JABC can be non-zero for some tripartite separable states. If so, that's actually kind of interesting because it can maybe it can tell some quantumness beyond the entanglement, what entanglement measure can tell for tripartite state. Yeah, thanks for the question.
I'm still somewhat confused by the 1 + 1D result in when there's a chiral central charge. When there's a chiral central charge, I mean, you cannot define rho A, B, and all that, right, because of the gravitational anomaly. So I guess my question is, when you write this formula, do you really have in mind a genuine 1 + 1D CFT with gravitational anomaly, or do you have in mind having some 1 + 1D gapless degrees of freedom living at the edge of a 2 + 1D bulk? The latter I can make sense of, but for the former, I don't understand what this formula means.
Yeah, good. Yeah, okay. I think I can safely rephrase Shuhan's question as a question for this reference. So for them, so at least for the author of that paper, it turns out that it makes sense to them to define the entropy for chiral CFT. But I totally agree that maybe we don't really need those chiral CFT, because you see for the free fermion system we simulate, they are not chiral CFT. They have both left movers and right movers. Yeah, Egan created some chiral thermal state on that non-chiral CFT. And again, for the study of the edge of the 2 + 1D chiral topological order, we didn't really make direct connection to chiral CFT either. Why? Because after doing the partial trace of the state, we end up with something effectively 1D, and it's non-chiral CFT. It's just that it's in a chiral thermal state, so there's some imbalance between the temperature of the left movers and the right movers. That's what's really if we want to understand the edge of topological order, I think that's enough. And further support to Shuhan's point is that, but I'm not saying people cannot define the entropy. Maybe formally it can do. We talked to some very formal QFT people doing some using operator algebra. They tell us that there's no much difficulty in defining chiral CFT, but indeed the definition of entanglement entropy is more subtle. But
chiral CFT is still fine. I thought the issue is entanglement.
Yeah. Oh, good. So yeah, maybe you can tell me the.
Because you cannot cut it, not cut the boundary condition. So it's not clear.
Oh, okay. Yeah. Tell me the reference. Yeah, maybe that's something contradicting with the reference, or maybe it's something more subtle. But let me point out one further thing. So this formula over here, so 2 eta minus 1. Yeah, this thing actually tells us some subtlety of the chiral CFT. Like, so suppose ABC is the whole interval, the whole circle. Then this formula tells us it gives us the formula gives us pi over 6 C minus, so it's non-zero for chiral CFT. But I said that for any pure state, J must be 0. But that for that to be true, we need some tensor product of the Hilbert space. So so if you believe our formula and the conclusion would be there's no tensor product structure for the chiral conformal field theory. So there's no effective theory of chiral CFT with tensor product Hilbert space. Those are related, but I don't think that directly answer your question.
Okay, if there are no further questions, let's thank Bowen for